Hello, welcome to Brunai Math Club. In this video, we study the transpose of a matrix and its properties. Okay, let's start. First, let's define the matrix transpose. Suppose we have a matrix. Its transpose is denoted A T or top. And this is defined by swapping the rows and columns. Okay, so that means the ij element of A transpose is the ji element of the original matrix A. So if we have a matrix such as A11, A12, and so on, A1n, A21, A22, and so on, A2n, and so on, AM1, AM2, AMn. So this is an m by n matrix. If we transpose it, what we get is this. The first row becomes the first column. So A11, A12, and so on, A1n. And the second row becomes the second column. A21, A22, and so on, A2n. And the last row becomes the last column. AM1, AM2, and so on, AMn. So as a result, we get n by m matrix. So that's the definition of the transpose. Let's see a few examples. Suppose we have matrix A, which is, let's say, 2, 4, 6, 1, 2, 3. So this is a 2 by 3 matrix. A transpose is a 3 by 2 matrix. That is, so the first row becomes the first column, so 2, 4, 6. And the second row becomes the second column, that's 1, 2, 3. Another example, if we have a row vector, let's say C, 1, 2, 3, its transpose is a column vector, 1, 2, 3. And if we have a column vector, let's say A is 0, 0, 1, then its transpose is a row vector, 0, 0, 1. Now, let's see some basic properties of matrix transpose. First is this. The transpose of a transpose is the original matrix. That is, A transpose is equal to A. Okay, let's show this. To see if two matrices are equal, like this, first thing we have to check is that their sizes are the same. Okay, so if A is an m by n matrix, then A transpose is an n by m matrix. If we take the transpose of that, then we should have A transpose. So we should swap these rows and columns, so it should be m by n matrix. So their sizes are the same. Next, we need to check that the corresponding elements in the two matrices are the same. So A transpose transposes ij element. So first, by definition, this is equal to, so the matrix inside here is A transpose. And A transpose ij element should be equal to A transposes ji element. And by the definition of transpose again, the element of ji element of A transpose is equal to A ij element. So the ij element of A transpose is equal to the ij element of A. That means their corresponding elements are always the same. Therefore, we have this equality, and we are done. Next, let's show the transpose of a sum is equal to the sum of transposes. First of all, addition between matrices doesn't change the size of the matrices, so the size check is okay. Let's check the corresponding elements. A plus B transpose, its ij element is equal to, by the definition, it's the ji element of this matrix inside. So that is A plus B ji. And by the definition of matrix addition, this is equal to A ji plus B ji. So that is the ij element of A transpose plus the ij element of B transpose. Therefore, this equality holds, and we are done. And next, let's show that the transpose of a scalar multiple of a matrix is equal to the scalar multiple of the matrix transpose. Okay, A is a scalar. That means it's just a number. First, it's obvious that their sizes are the same, so let's check the elements. Ka transpose ij element is by definition Ka ji element. And by the definition of scalar multiplication of a matrix, this is equal to Ka ji. But this one is the transpose element. So Ka transpose ij. Therefore, this equality holds, and we are done. Okay, next, let's show the transpose of a matrix product is equal to the product of matrix transposes, but the order is reversed. First, let's check the sizes. Okay, let's say A is L by M matrix and B is M by N matrix, because we're assuming that this product makes sense. So their sizes must match. That means the number of columns in A should match the number of rows in B. Okay? So as a result, AB is an L by N matrix. Okay? So that means AB transpose should be N by L matrix. Okay, now A transpose is an M by L matrix, and B transpose is an N by M matrix. So we can define the product between B transpose and A transpose in this order, because the number of columns in B transpose is M and the number of rows in A transpose is M, so we can multiply them. So B transpose times A transpose is N by L matrix. So the sizes match. Next, let's show the equality between the corresponding elements. So A, B transpose, its ij element is equal to A, B, J, I elements. And by the definition of matrix multiplication, this is equal to sum over k from 1 to m and a j m, it's not m, it's k, times b k I. And since they are just numbers, we can always swap the order. Let's do it. And this is b ki times a j k. But this one is the ik element of B transpose, right? So it's B transposes ik element. And similarly, this is the kj element of A transpose. Now look at this. We have k here as the second index of B transpose and k here as the first index of A transpose. So this is nothing but the ij element of the product between B transpose and A transpose. So B transpose A transposes ij element. So the ij element of AB transpose is equal to the ij element of B transpose A transpose. And we are done. Let's see an example of this last theorem. Let's say A is a 2 by 3 matrix, 2, 4, 6, 1, 2, 3, and B is a 3 by 2 matrix, 1, 3, negative 2, 0, 0, 2. So we want to see that AB transpose is equal to B transpose A transpose. So first let's calculate AB and take the transpose of it. So this is this times this, which is, if you calculate it, it should be, let's see, negative 6, 18, negative 3, and 9. So finding this is an exercise. So AB transpose is negative 6, 18 here, and negative 3, and 9. Now, A transpose is, so 2, 4, 6, 1, 2, 3, and B transpose is, it's a 2 by 3 matrix. So 1, 3, negative 2, 0, 0, 2. So B transpose A transpose is this times this, which should be equal to, actually we already know the answer. If you calculate it, you should get negative 6, negative 3, 18, 9. Okay, finally, let's find what we have for this. A, B, C transpose. A, B, C are matrices. Okay, to find this, we use first associativity of matrix product. So this is equal to, for example, AB. So first we multiply A and B first, then multiply C and transpose. So this is one matrix and this is another matrix. So this is a product between two matrices. So that is, by the theorem we have just proved, is equal to C transpose and AB transpose. Now we apply the theorem again to this part. So that is C transpose, B transpose, A transpose. And from the associativity of matrix product, we can remove these parentheses. So that is C transpose, B transpose, A transpose. So the product of matrices, if we take its transpose, then we always get the product of transposes, but the order of product is reversed. Okay, that's it for this video. See you later. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.